Practical exercise 3. In this exercise, we worked with complex digital circuits which demanded both excellent spatial organization on the breadboard and better knowledge of the binary addition system.
Part 1. Demultiplexer.
In the first part, we built a circuit using an IC known as a demultiplexer. A demultiplexer is a digital switch with a single input and multiple outputs. We chose particular inputs by using binary addition, with the push buttons as binary digits values 1 or 0. The demultiplexer that we used had 4 inputs and 16 outputs. We had 4 buttons as inputs and 8 LEDs to show which input led to its output. We connected the LEDs to the first 8 outputs 1 to 8 to fill out the first truth table. Then we switched the LEDs to outputs 9 to 16 and filled out the second truth table. The truth tables that we used had first binary values 0 to 7 and then 8 till 15, where each binary value has a different combination of inputs. When we connect the LEDs to the ground rather than the VCC, the opposite happens. All the LEDs light up and we can turn off an LED with an equivalent binary value to the push button input.
Part 2. The 555 timer circuit. The 555 IC is an 8-pin integrated circuit that is capable of producing accurate time delays and oscillations. In this part, we built a 7-segment display driven by a 555 timer and a 4-bit counter, where the 555 timer will be generating clock pulse. These pulses pass to the 4-bit counter, which is then displayed on the 7-segment display. When the circuit is disconnected to the push button, the circuit will display the number of pulses going through the 4-bit counter from 0 to 9, going back to 0 after the 9. If we change the capacitor in the circuit, the frequency of the pulses will also change. The relationship between the frequency, capacitor, and the resistor can be seen in the equation. If we now connect the push button just to pin 2, which is the clock inhibit on the 4026 IC, and the push button is held down, it will let 5 voltage go through and stop the clock pulse being sent to the IC, and therefore freezing the value on the 7-segment display. Next, we also connect the push button to pin 15 or the reset on the IC 4026. So the button is pressed, it will let the 5 voltage through and reset the counter to 0. Part 3. The shift register. When we push the button very quickly, we got 2 results. That is because when the button is pushed for a single such pulse, the clock is either low or high. If the clock is on high, the LEDs turn on one at a time, but if it's low, nothing happens. But when we held the button down for 1 clock pulse, the shift register worked so the first LED turned on, and then after that 1 LED at a time turned on after another. When we pushed the button for 2 clock pulses, both LED 1 and LED 2 turned on. After we stopped pushing, LED 1 turned off and LED 3 turned on, and then LED 2 turned off and LED 4 turns on. This happens because when LED 1 turns off, LED 2 sends a signal to LED 3, and so on. When we push the button for 4 clock pulses, all the LEDs turn on and then turn off when we stop pushing, first LED 1 and so on. When we push the button for 2 clock pulses with 1 gap in between, first 1 clock pulse, paused and then pushed for another clock pulse, this led to a gap between the LEDs, which can be expected because when you push the button for a clock pulse, the values from the input are stored in flip-flop memory state. Then each flip-flop stage triggers the transfer of each bit to the next flip-flop stage. Practical Exercise 4, PPG. In exercise 4, we use the PPG to detect blood volume changes in our fingers. But what is a PPG? The cardiac cycle creates a pressure pulse in the subcutaneous tissue. The pressure pulse causes a change in volume in the blood vessels in the finger, which is detected by illuminating the skin with an infrared light from an LED and then measuring the amount of light either transmitted or reflected to a photodetector. Oxygenated hemoglobin absorbs infrared light, so the photodetector will pick up the light that scatters off the deoxygenated hemoglobin in the vessels in the finger. The signals from the infrared detector can be split into a DC and AC component. The DC component is from the bulk absorption of the skin tissue, and the AC component is from the changes in blood volume in the skin caused by the pressure pulse of the cardiac cycle. In this exercise, we constructed a circuit which filters infrared signal and translates the AC component peak to light an LED, which will indicate the person's heartbeat. First, we set up and tried out our reflective optical sensor. We tried it out with our instructor's phone harnesses because we all have iPhones which cameras don't detect infrared light. In part 1, we calculated which resistor and which capacitor we will use for the active high-pass filter with a 0.7 Hz cutoff frequency. We used the equation on the practical paper to calculate the resistor and capacitor and solved for the 47 k ohm resistor and the 4.7 microfarad capacitor. For the low-pass filter, we could calculate R1 and 2 from the given signal gain, which was 101. We calculated that R2 was the 680 k ohm resistor and R1 was the 6.8 k ohm resistor. And from that we could calculate the capacitor, which is the 100 nanofarad one. Then we built a double filter circuit to amplify the low signal. After some testing, we figured out that having the potentiometer in 500 ohms worked the best. The signal from Álfheiður was always very good, versus Arnar's signal was always pretty bad. The reason could be because the build of the circuit was more convenient for Álfheiður than Arnar's, and Álfheiður's blood flow to the fingers could be better than Arnar's.
Now that we have successfully built a PPG, it would be nice to keep track of our heartbeats and do a little experiment using our device. To count and keep track of our heartbeats, it's best to have a decade counter on a device. So we will use the circuit we built in Practical 3, but replace the 555 timer with the PPG, so our heartbeat will act as a pulses from the 555 timer, and add another 7-segment display and another 4026 IC, which will control the second display. The first 4026 IC will be connected to the second one from pin 5 to pin 1, but pin 5 is the carryover output pin of the IC and produces a pulse after counting to 9. The pulse goes to the clock on the second IC. This carryout only happens if the 4026 IC is connected to another 4026 IC. To be able to start a new heart rate recording without turning off the device, we also added a single push button which we connected to the restart pins on both ICs, so the count would start again at 0, and now the PPG is ready for the experiment. Our experiment focused on the change in heart rate before and after a simple exercise, including 10 sprints and 10 burpees. We started off by taking 3 recordings of each member's resting heart rate in beats per minute with our own device. Next, we recorded each member's heart rate after he'd done an exercise, where we took 3 recordings with a pause in between exercises to get a resting heart rate again.